Right now, somewhere in your kitchen, there is a cup of coffee going cold. You didn't do anything to it. You didn't touch it, stir it, or curse it under your breath for the 100th time this month. It is simply losing its heat into the room, second by second, molecule by molecule, until it matches the temperature of everything around it. And here's the strange part, the part most people never stop to consider. This will never reverse. The coffee will never spontaneously pull heat back out of the air and become hot again. Not in 1,000 years. Not in 1,000,000,000,000. Not if you waited for the sun to die and a new one to be born in its place. The universe has a rule, and that rule is so absolute that physicists consider it more reliable than gravity, more certain than the speed of light, more dependable than anything else we know about reality. It is called the second law of thermodynamics, and in one sentence, it says this: everything tends toward disorder. Most people hear that and shrug. Disorder. Fine. Rooms get messy, things break, people get old. It sounds like a minor inconvenience, the kind of thing you'd find on a poster in a tired office break room. But this single principle is not just describing your coffee or your bedroom or the junk drawer you keep meaning to clean out. It is describing the future of everything that exists. It is describing the slow, irreversible unraveling of every star, every galaxy, every memory, every thought you have ever had, every civilization that has ever risen and called itself permanent. And if you follow it far enough into the future, far past anything a human mind was built to comfortably hold, it leads somewhere almost impossible to imagine, a universe so spread out, so cold, so utterly without structure, that it will have forgotten it ever contained anything at all, including us, including everyone who ever lived, loved, built, and died, believing they mattered. This is not a metaphor. This is physics, and it is coming for everything, including the very stars that gave you the atoms in your body. To understand how something this enormous starts with something this small, we need to go back to a quiet, obsessive man with a notebook and a single idea that quietly broke physics in half. The man who counted disorder before the 19th century. Physicists thought about heat the way you might think about water flowing downhill. It was Sadi Carnot, a French engineer studying steam engines, who first noticed something curious. Heat always flows from hot objects to cold ones, never the reverse, and you can never convert all of that heat into useful work. Some of it always escapes, always wastes away, always goes somewhere you can't get it back from. Carnot didn't have the full picture, but he had found the edge of something important. A few decades later, a German physicist named Rudolf Clausius gave that wasted, escaped, unusable energy a name. He called it entropy, from a Greek word meaning transformation, and he proposed almost as a quiet aside that in any isolated system, entropy can only increase. It cannot go down, ever. But it was an Austrian physicist named Ludwig Boltzmann who took that vague, almost philosophical idea and turned it into something you could count, something you could put a number on. Boltzmann's insight was deceptively simple, the kind of idea that seems obvious only after someone else has already had it. Before Boltzmann, the fundamental laws of motion were symmetric in time. If you filmed two billiard balls colliding on a table and played the footage backward, the laws of physics governing their motion wouldn't object. Both directions looked equally valid, equally legal, equally consistent with Newton's equations. And yet nobody has ever seen a shattered wine glass leap up off the floor and reassemble itself on a table. Nobody has watched a plume of smoke pour itself back down into a chimney. Nobody has seen an old man grow younger by eating a cake that unbakes itself in his stomach. Somewhere between the tiny, reversible rules governing individual atoms and the large, irreversible world we actually live in, a direction appeared. Time started pointing somewhere, and nobody could explain why. Boltzmann's answer was this: it's a numbers game. It has nothing to do with any law forbidding the reverse process, and everything to do with probability. Imagine a box containing 1,000 gas particles, split cleanly in half. 500 particles of blue gas crowded into the left side, 500 particles of red gas crowded into the right side, with a thin, perfectly clean line dividing them. There is exactly one way, out of all the possible arrangements of those particles, to have that specific, neat division. Now remove the imaginary wall and let the particles move randomly, the way gas always does, bouncing and colliding according to nothing more exotic than chance. How many ways are there to arrange 1,000 particles so that they're thoroughly, randomly mixed, no clean split, No order, just chaos? The number is so large it stops meaning anything intuitive to a human brain. It isn't twice as many ways. It isn't 1,000 times as many ways. It's more like the difference between a single grain of sand and every grain of sand on every beach on Earth, multiplied by itself more times than there are atoms in your body. Disorder isn't winning because the universe has some preference for chaos, some cosmic mood for mess. Disorder is winning because there are catastrophically, almost unimaginably more ways to be disordered than to be ordered. Order is rare. Order is a needle in a haystack the size of a galaxy. Mess is common. Mess is the default. Mess is what you get almost automatically when particles are free to move and nothing is actively stopping them. And when something moves randomly enough times, statistics will always eventually drag it toward the more common state, simply because there are vastly more roads leading there than roads leading back. This is entropy, properly defined, not the lazy casual version that gets thrown around to mean stuff falling apart, but a precise measurable quantity describing how many different microscopic arrangements of particles could produce the same overall observable state. Low entropy means very few possible arrangements correspond to what you're looking at, which means extremely high specificity, which is what we experience and call order. High entropy means an enormous number of possible arrangements would all look the same from the outside, which is what we experience and call disorder, or randomness, or mess. And the second law of thermodynamics says, with the same unwavering confidence we'd use to say the sun will rise tomorrow, that the total entropy of a closed, isolated system never decreases over time. It either increases, or, in the rarest and most fleeting moments, stays exactly the same. It never, ever goes the other way. Once Boltzmann put a number on it, the entire mystery of time's arrow suddenly had an explanation that didn't require any new law of physics at all. The future doesn't look different from the past, because some rule forbids the past from happening twice. The future looks different from the past, because the future is overwhelmingly, statistically, mathematically more likely to be messier than the past was. We remember yesterday, and not tomorrow for the same fundamental reason. A shuffled deck of cards is far more likely to be in a random order than in a perfect sequence. There are simply more ways for the world to be messy than for it to be neat, and the world, given enough time, drifts toward whatever has more ways of happening. It's a strange thought to sit with. The entire one-directional flow of your life, the fact that you can remember your childhood, but not your future, the fact that broken things stay broken, unless something actively repairs them, all of it traces back to nothing more mystical than counting. The universe isn't pushing time forward with some hidden hand. It's simply wandering, randomly, through an almost infinite space of possible arrangements, and there happen to be vastly more disordered arrangements than ordered ones waiting on the other side of now. The tiny demon who tried to cheat physics. Almost as soon as the second law was written down, physicists started looking for loopholes, because that's what physicists do. In 1867, the Scottish physicist James Clerk Maxwell proposed a thought experiment specifically designed to break the rule. Imagine a sealed box divided into two halves by a wall with a single tiny door, and imagine a microscopic, intelligent being standing at that door, watching individual gas molecules approach. Every time a fast, hot molecule approaches from the left, the being opens the door and lets it through to the right. Every time a slow, cold molecule approaches from the right, the being lets it through to the left. Given enough time, without adding any energy to the system in any obvious way, this tiny gatekeeper could sort a uniformly mixed gas back into a hot side and a cold side, manufacturing order out of disorder, seemingly for free. Physicists started calling this hypothetical creature Maxwell's demon, and for decades it sat in the back of physics like a splinter nobody could quite remove. The eventual resolution, worked out across the 20th century by physicists including Leo Szilard and later Rolf Landauer, turned out to be one of the most important discoveries linking physics to information itself. The demon isn't actually free. In order to decide whether a molecule is fast or slow, the demon has to measure it, has to gather information about it, and that act of measuring and then erasing the memory of the measurement to make room for the next one costs energy, and that energy cost generates exactly enough entropy elsewhere to keep the books balanced. The second law doesn't just govern heat and gas particles, it governs information itself. Knowing something, remembering something, forgetting something in order to make room for a new thought, all of it has a thermodynamic price tag, paid in the same currency that powers stars and ages bodies. Your brain isn't exempt from this. Every memory you form, every thought you have, every fact you forget to make room for tomorrow's experiences is a tiny transaction in the same universal ledger that governs the death of stars. You are a statistically improbable event. Now here is where it stops being abstract, where it stops being something that only happens in a sealed box of gas particles in a physics classroom, and starts being deeply, uncomfortably personal. You, reading this sentence right now, are an extraordinarily improbable arrangement of atoms. Your body maintains something on the order of 7 billion atoms, organized into cells, organs, neural pathways, and fleeting electrochemical patterns we call thoughts, all of them working in active, continuous defiance of the statistical tide that the second law describes. You are not a passive object drifting through entropy. You are a machine built specifically to fight it, moment by moment, for as long as you're alive. Every breath you take pulls in oxygen, a relatively ordered, energy-rich molecule, and uses it to power thousands of biochemical processes that keep your cells repairing themselves faster than they break down. Every meal you eat is, in a very real thermodynamic sense, an act of borrowing order from the world around you. Plants capture low-entropy sunlight and convert it into high-energy, organized sugar molecules. You eat the plant, or you eat something that ate the plant, and you cash in that borrowed order to keep your own internal disorder temporarily, locally at bay. This is what biologists call metabolism, and what physicists, if they're being precise, call a localized temporary reversal of entropy's pull, paid for by importing order from somewhere else and exporting waste heat and disorder back out into the environment. You are not breaking the second law when you stay alive. You are simply moving the bill somewhere else, the same way an air conditioner cools a room by dumping heat outside it. But the negotiation, no matter how skillfully managed, no matter how many vegetables you eat, or how many hours you sleep, eventually ends. Cellular repair mechanisms slow down. DNA accumulates small, uncorrected errors with every replication, a process called mutation load. Proteins misfold and clump together instead of doing their jobs properly. Mitochondria, the tiny structures inside your cells responsible for converting food into usable energy, become less efficient, leak more damaging byproducts, and produce less of the fuel your body needs to keep fighting disorder. Slowly, and then all at once, the arrangement that was specifically uniquely you loses its improbability and dissolves back into the much larger, much more common pool of less organized, less specific configurations. We have a word for that moment, the word we use at funerals, the word that makes a room go quiet. We call it death. But physics, with its characteristic lack of sentimentality, has a more honest word for it: equilibrium. The state where there is no longer a meaningful difference between you and your surroundings, no temperature gradient, no chemical gradient, no ongoing fight. Just matter, finally settling into whatever the most probable arrangement happens to be. It's worth sitting with that for a moment, uncomfortable as it is, because it quietly reframes something we usually treat purely as personal tragedy into something far larger. The same pattern playing out at the largest scale anyone has ever measured. Aging is not a malfunction, a bug in an otherwise perfect system. It is entropy, patiently, indifferently doing to a human body exactly what it does to every other organized structure in the universe, given enough time. Your skin doesn't wrinkle because something has gone wrong. It wrinkles because something was always, eventually, going to happen, the same way every other locally ordered system in the cosmos eventually loses its fight against the statistical tide, pulling everything toward disorder. Civilizations borrow time, then pay it back, and it doesn't stop with a single body. Zoom out from one organized human to an entire organized civilization, and the exact same pattern repeats itself at a much larger scale. Just slower, just quieter, just easier to miss while you're living inside it. Empires rise because, for a while, a group of humans manages to organize energy, labor, agriculture, and information into something significantly more ordered than its surroundings. A structure capable of resisting collapse longer than the chaos around it would naturally allow. Rome built aqueducts that moved water across hundreds of miles using nothing but gravity and precision engineering. Ancient Egypt organized enough labor and enough surplus grain to build structures that have outlasted every government that has existed since. The Maya tracked celestial cycles with an accuracy that wouldn't be matched by European astronomy for over 1,000 years. Each of these civilizations represented an enormous, costly, temporary local victory against disorder achieved through irrigation systems, written language, trade networks, and the simple, brutal organization of human effort into a sustained structure. But every single one of these civilizations, without a solitary exception in the historical record, eventually returned that borrowed order to the soil. Rome's aqueducts cracked, silted up, and stopped flowing. Egyptian temples were buried under centuries of wind-blown sand, their carved hieroglyphics worn smooth by weather, long before anyone could read them again. Mayan cities were swallowed by jungle so completely that explorers stumbled onto pyramids they mistook for hills. Stone columns that once held up temples dedicated to gods people were certain would last forever now hold up nothing but tourists' cameras and the occasional pigeon. Languages spoken fluently by millions, languages that carried entire mythologies, legal systems, and ways of understanding the world, fall silent because the last living speaker dies, and nobody learns the words afterward. Civilizations aren't conquered by entropy in any dramatic single moment, the way a sandcastle is conquered by a wave. They're loaned a brief exemption from it, an exemption purchased through the relentless input of organized human energy, agriculture, and labor, and eventually, when that input slows, fragments, or gets disrupted by drought, disease, war, or simple administrative collapse, the loan comes due. Disorder doesn't have to attack a civilization, it just has to wait. It always wins eventually. Not because it's stronger in any active sense, but because maintaining order requires constant, expensive effort, and disorder requires none at all. It is the default state of everything left unattended. This is, in some sense, the most underappreciated lesson, buried inside the second law. Nothing organized maintains itself for free. Not a body, not a civilization, not a star. History is full of smaller, sharper examples of the same lesson, almost as if the universe keeps writing the same sentence in different handwriting. The Library of Alexandria, once the largest concentration of organized human knowledge anywhere on the planet, scrolls upon scrolls representing centuries of careful collection and copying, did not need to be destroyed in one dramatic fire to disappear. Neglect, funding cuts, and the slow attrition of unmaintained buildings did most of the work over time, the same way unattended order always dissolves. The Indus Valley Civilization built some of the most sophisticated urban planning of the ancient world. Cities with covered drainage systems, more advanced than many cities would have for thousands of years afterward, and yet a shift in monsoon patterns and the slow drying of a river was enough to unravel an entire urban culture within a few centuries. On Easter Island, a society organized enough to carve and move multi-ton stone statues across miles of terrain found that organization alone wasn't a permanent shield against resource depletion. Order, no matter how impressive at its peak, was never the default. It was always the exception, propped up by continuous, costly maintenance, and the moment that maintenance faltered, the underlying statistical tendency toward disorder simply resumed, exactly as it always does. The slow death of stars zoom out again, past the lifespan of empires, past the lifespan of entire species, into the lifespan of stars themselves, and you find that even the most powerful, most violent, most seemingly eternal objects in the sky are bound by exactly the same arithmetic. Our sun is, right now, in the most stable, most ordered phase it will ever experience in its multi-billion-year life. Deep in its core, immense pressure and temperature force hydrogen nuclei to fuse together into helium, a process called nuclear fusion, releasing the energy that has kept Earth warm enough for liquid water, and therefore life, to exist for billions of years. This fusion process is remarkably stable, held in a delicate balance between the inward crush of gravity and the outward push of the energy being released, a balance astrophysicists call hydrostatic equilibrium. It feels from where we stand permanent. It is not. The sun is burning through a finite reserve of low-entropy hydrogen fuel, and in roughly 5 billion years, that reserve will run critically low in its core. When that happens, The sun's core will contract under gravity, while its outer layers swell dramatically outward, and it will become what astronomers call a red giant, a star so enormous that its expanding atmosphere will very likely engulf Mercury, Venus, and possibly Earth itself, depending on exactly how much mass the sun sheds along the way. Eventually, having burned through everything it can fuse, the sun will shed its outer layers entirely, leaving behind nothing but a small, incredibly dense, slowly cooling core called a white dwarf, an ember of what used to be a star, radiating away its remaining heat into space for unimaginably long stretches of time, with nothing left to relight it. This isn't a special tragedy reserved exclusively for our sun. Every star, regardless of its size, follows some version of the same arc, just on different timescales and toward different endings. Stars far more massive than the sun burn through their fuel far faster, sometimes in only a few million years rather than billions, and end their lives in spectacular, catastrophic explosions called supernovae, briefly outshining entire galaxies before collapsing into either a neutron star, an object so dense that a teaspoon of its material would weigh roughly as much as a mountain, or, if the original star was massive enough, a black hole, a region where gravity has crushed matter so completely that not even light can escape its pull. Smaller stars, the dim, slow-burning red dwarfs that make up the majority of stars in our galaxy, will sip their fuel so conservatively that some of them are expected to keep faintly glowing for trillions of years, vastly longer than any sun-like star, before they too finally exhaust what they have and fade into cold, dark stellar remnants. But notice the pattern hiding underneath every single one of these different endings. Every star, no matter its mass, no matter how it dies, is converting low-entropy fuel into high-entropy waste. Exactly the same way your body converts food into waste heat. Exactly the same way a civilization converts organized agricultural surplus into eventual ruin. Stars are not eternal. Stars are simply very large, very slow, very patient demonstrations of the same statistical law governing your coffee cup. The universe stops making light. Here's the part that should genuinely, quietly unsettle you, the part that turns this from a story about individual stars, dying into a story about the death of light itself. Star formation is a temporary phenomenon in the history of the universe, not a permanent feature of it. Right now, we happen to be living during what astronomers sometimes call the stelliferous era, a period, cosmically speaking, where there is still enough diffuse hydrogen gas floating in interstellar clouds for gravity to pull it together, ignite it, and form new stars. This has been going on for roughly 13.5 billion years already, ever since the very first stars lit up in the young universe. But that hydrogen supply, vast as it seems, is finite, and every star that forms permanently locks some fraction of that hydrogen away into heavier elements through fusion, elements that don't easily convert back into star-forming material. Each generation of stars leaves behind slightly less raw material for the next generation to use. Estimates suggest that star formation will slow dramatically and eventually stop entirely somewhere between 1 trillion and 100 trillion years from now, depending on exactly how efficiently galaxies recycle their remaining gas. After that point, no new stars will ever ignite again, anywhere, for the rest of cosmic history. The universe will be left only with the stars that already exist, slowly burning down one by one, like the last embers of a campfire nobody is feeding anymore. Small red dwarfs will be the last to go, sipping their fuel for trillions of years before finally dimming into cold, dark stellar corpses. And once the very last red dwarf exhausts its hydrogen, the universe enters what astronomers call the degenerate era, a cosmos populated only by the leftover remnants of dead stars, white dwarfs, neutron stars, and black holes, drifting through an increasingly empty, increasingly dark expanse, with no new light being produced anywhere, by anything. Ever again, try to actually picture that for a second. Trillions of years of total, absolute darkness between the rare points of dim, fading stellar embers, light years apart, slowly cooling toward the temperature of the space around them. The universe's lights going out permanently, one ember at a time, with absolutely nothing left capable of relighting them. When matter itself stops being matter, but even the dead, cooling remnants of stars aren't the end of the story. Because nothing escapes entropy's timeline, not even the things we usually think of as the most permanent objects in existence. Atoms themselves, white dwarfs and neutron stars, will continue existing for a staggeringly long time after the last star burns out. But theoretical physics suggests that even matter itself may not be permanent on a long enough timescale. Some models in particle physics, though not yet experimentally confirmed by any laboratory on Earth, predict that protons, the very particles that make up the nucleus of every atom, may eventually decay into lighter particles. If this prediction turns out to be correct, then given enough time, somewhere on the order of 10 to the 34th, up to 10 to the 41st years, a number so large it has essentially no meaningful comparison ordinary experience, ordinary matter would begin quietly dissolving. The atoms making up the leftover white dwarfs, the atoms making up dead planets and asteroids and cold rock floating in the dark, the atoms that, billions of years earlier, briefly made up you, would, on these almost incomprehensible timescales, simply stop being atoms at all, breaking down into lighter particles and radiation, scattering outward into an increasingly empty universe. It's worth pausing here to notice something. This isn't destruction in any violent, dramatic sense. There's no explosion, no final crescendo. It's something closer to a whisper, an impossibly slow unraveling that no observer could ever witness happening. Because by the time it happens, there would be no organized structure left anywhere capable of observing anything. Even black holes are not forever, and black holes, the most extreme, most violently powerful objects in the known universe, regions where gravity has become so intense that it warps space and time themselves, where not even light, the fastest thing in existence, can escape once it crosses the boundary called the event horizon, turn out to not be permanent either. In the 1970s, the physicist Stephen Hawking demonstrated something that initially seemed almost paradoxical. Black holes, despite their reputation as cosmic vacuum cleaners that swallow everything and release nothing, actually leak a faint stream of radiation and slowly lose mass over time. This phenomenon, now called Hawking radiation, arises from strange effects at the very edge of the event horizon involving quantum fluctuations in empty space, and it means that every black hole, no matter how massive, is technically evaporating, one infinitesimally small particle at a time. For the supermassive black holes that sit at the centers of galaxies, ones containing the mass of millions or even billions of suns, this evaporation process is almost unimaginably slow. It would take far longer than the current age of the universe, repeated many times over, for even a modest black hole to fully evaporate. But on the kind of timescale we're discussing here, a timescale where we've already passed through trillions of years of star formation, trillions more of stellar remnants slowly cooling, and unimaginable stretches where matter itself decays, even black holes eventually run out their clock. Somewhere around 10 to the 100th years, give or take, the very last and most massive black holes in the universe will have radiated away every last bit of their mass, releasing it as faint, scattered radiation, and then they too will simply cease to exist. Once that happens, there is nothing left. No stars, no stellar remnants, no atoms, no black holes, nothing organized anywhere, at any scale. A universe that stretches faster than it can be crossed. There's another piece of this story that makes the ending even stranger, and it has nothing to do with stars burning out or atoms decaying. It has to do with space itself. In the late 1990s, astronomers studying distant exploding stars, called supernovae, discovered something nobody expected. The expansion of the universe isn't slowing down under its own gravity, the way everyone assumed it should be. It's speeding up. Something is pushing galaxies apart from each other at an accelerating rate, and physicists have given that mysterious something a placeholder name: dark energy. Nobody fully understands what dark energy actually is, at a fundamental level, but its effect is measurable, consistent, and, as far as current observations can tell, permanent. This accelerating expansion continues indefinitely, which current evidence suggests it will. Then galaxies that aren't already gravitationally bound together will get pulled apart from each other, faster and faster, eventually crossing a threshold where the space between them is expanding faster than light could ever cross it. Distant galaxies wouldn't just become too far away to reach. They would become permanently, physically unreachable, their light forever unable to catch up to us, fading from view one by one until, from the perspective of any single remaining galaxy, the rest of the universe simply disappears into darkness. long before the stars inside that galaxy even finish burning out. This means the universe isn't just running out of fuel internally. It's also tearing itself apart spatially, stretching the distance between everything that exists until isolation becomes the default state of the cosmos. Long before heat death technically arrives, the Dark Era pushed the clock forward to somewhere around 10 to the 100th years, a number so large it has no real intuitive meaning to a human brain evolved to track seasons and lifespans, not cosmic epochs, and physicists describe a possible final state of the universe called heat death, or sometimes, more poetically, the Dark Era. By this point, every black hole has evaporated, every proton has decayed, every star has gone permanently dark. Matter, in any organized recognizable form, has stopped existing entirely. What remains is an unimaginably thin, unimaginably cold soup of photons and fundamental particles spread across a universe that has expanded so dramatically that the average distance between any two particles is vastly greater than the size of our entire observable universe today. Temperature differences, the one essential ingredient required for anything to happen, anywhere, ever, will have flattened completely to nothing. No more heat flowing from hot regions to cold regions. No more energy gradients available to do any kind of work, push any kind of process, drive any kind of change. No more chemistry, no more physics in any sense that produces events. Just an infinite, featureless calm, stretching outward in every direction, forever. This is the part that deserves to be said as plainly and directly as possible, because it's the actual heart of this entire story. Information requires structure, and thought requires information. A brain, a memory, a single fleeting conscious thought. All of them are organized patterns, low-entropy arrangements actively doing work against the statistical tide, exactly like your body fighting off cellular decay, exactly like a star fighting off gravitational collapse through fusion, exactly like a civilization fighting off the jungle and the sand and the silence through constant maintained effort. In a universe that has reached true heat death, there is no structure left anywhere capable of holding a thought. Not a human thought, not an alien thought, however different its biology or chemistry might have been. Not any thought, by anything, anywhere, for the rest of time. The universe will not be sad about this ending, because sadness is also a structured, organized process requiring a brain, or something functionally equivalent to a brain, and structured, organized processes will be the very first thing gone. The universe will not know in any sense that it ever held galaxies, stars, oceans, ideas, or a single person who once stood in a kitchen, mildly annoyed, wondering why their coffee had gone cold again. It will have, in the most literal, physical, measurable sense, forgotten everything it ever was. Not metaphorically forgotten, actually physically forgotten, because the structures capable of remembering anything will have ceased to exist. The strange comfort hiding inside the ending, and yet, here is where the story turns, because there's a strange, quiet comfort hiding inside this bleak arithmetic, if you're willing to actually look for it instead of flinching away from it. The fact that the universe trends inevitably toward forgetting is precisely what makes the brief moments of remembering so strange, so rare, and so genuinely worth paying attention to. You exist during the stelliferous era, the cosmic blink when stars still burn, when chemistry still works, when atoms can still arrange themselves into something complex enough to ask questions about its own existence. Out of roughly 10 to the 100 years of total cosmic history, that physicist's project lies ahead. Intelligent life capable of understanding any of this, capable of even formulating the question of what entropy means, has existed for perhaps 10,000 years so far. A sliver of a sliver, a number so small relative to the total timeline that it is statistically almost indistinguishable from never having happened at all. And yet here you are, reading this, thinking about heat death and entropy and Boltzmann's particles and dying stars, using a brain made of atoms that briefly, improbably, against overwhelming statistical odds, decided to organize themselves into something capable of caring about what eventually happens to all the other atoms in existence. There's an idea, one that echoes through how physicists like Richard Feynman talked about science and meaning, that the universe doesn't need a reason to be remarkable, and that meaning doesn't require permanence in order to be genuinely real. A flower doesn't need to bloom forever to be worth stopping and looking at while it blooms. If anything, Knowing that it won't last very long is exactly what makes someone slow down and actually pay attention to it instead of walking past. The same logic scales up to absolutely everything we've talked about. Your life is not somehow less meaningful because it eventually ends. Civilizations are not pointless simply because they eventually fall into ruin and get reclaimed by sand or jungle. Stars are not wasted simply because they eventually burn out and go dark. The entire universe is not a tragedy simply because it's heading very slowly toward heat death. These are simply the terms of the deal that existence itself runs on. Order is rare, temporary, and statistically improbable everywhere it appears in the cosmos, and that rarity is exactly what makes it remarkable wherever it shows up. Whether in a star fusing hydrogen, in a single living cell repairing its own DNA, or in a sentence being read right now by a mind capable of actually understanding what it means. Consider, too, what this means about the act of remembering itself. Every memory you hold, every photograph, every story passed down from a grandparent, every word carved into stone by people who knew, on some level, that stone erodes too, is a tiny local act of defiance against the universe's overwhelming statistical tendency to forget. You are not just living inside Entropy's story. You are, in your own small and temporary way, pushing back against it. Every single time you choose to remember something, write something down, teach something to someone younger than you, or simply pay attention closely enough to notice that your coffee is getting cold. The cup, one last time, so the next time your coffee goes cold while you're distracted by your phone or lost in thought at your desk, you might think about it differently than you used to. Not as a small, mildly annoying inconvenience, but as a tiny, perfect, everyday demonstration of the exact same law that will one day, unimaginably far in the future, quietly extinguish every star, dissolve every atom, and evaporate every black hole in existence. You are watching, in miniature, on your own kitchen counter, the largest, most certain, most universal pattern in the entire cosmos play out in real time. And for now, against unbelievable statistical odds, in defiance of nearly every probability working against you at every single moment, you are still here, still organized, still thinking, still capable of caring about a question this large. You exist in a universe that is very slowly, very patiently, with absolutely no malice and no awareness, forgetting itself one star, one atom, one black hole at a time. But it hasn't forgotten yet, and right now, neither have you.